Hello. Okay, welcome back to DSP. It's about time. And so today we are going to continue our lecture number 4, and the title is D2C conversion with as sync interpolation. So basically, I'm trying to communicate this idea to you that a D2C conversion is a kind of interpolation. And the interpolation function that we are going to be using or showing is the sync function. Okay, but before we move on, let's do a bit of a kind of outlook. We are going to finish chapter 4. Finish all I want to cover in chapter 4 of the textbook. 第4章 I'm going to finish it today and move on to chapter 5. So in chapter 4, in the end, you learn that we can start with a continuous time signal and put it into a C to D. D, just you can say it's digital, and but conceptually, the result is going to be a sequence of numbers, and which show up every integer multiple of sampling period t, right? And from there, we can do the opposite. So, but in between, the course is all about what's happening in between. So once xn becomes digital, we can start doing some computation, right? We can start changing it, processing it, and so so whatever in the middle is called digital signal processing. Whatever that comes in between, digital signal processing. So we have input, and after this processing, the output, if we denote it as YMN, then we are ready to go back to the analog domain by doing D2C conversion, DC. And typically, almost all the time, we assume that the sampling rate for D2C is the same as the sampling rate in C2D. So anyhow, the result is going to be now a signal back in the analog world. Okay, so that's the overall flow of signal processing. We have covered C2D in previous lectures, including quantization, right? And after becoming digital, now that's today's lecture. So let's say this is lecture 1, 2, and 3. It's all about C2D. Lecture 1 to lecture 3, that's C2D. And today we are going to cover lecture 4, that's D2C. And basically you will be using, we'll learn the reason why D2C conversion is a kind of interpolation. But now, coming out from next lecture, all about what's happening in between in the digital domain, right? So now we have chapter 5. So chapter 5 is going to focus on one specific kind of system by the name LTI, linear and time invariant. LTI, linear time invariant system by the name LTI. Okay? LTI systems, and we'll soon learn that in our very next lecture, chapter 5 also, lecture 5, you will learn that LTI systems can be, all you need to know about LTI systems are their impulse responses. So impulse responses, usually denoted by H of n, impulse responses. And then next lecture coming up is just for the purpose of computation, we will further focus on difference equations. Difference equations. Difference equations, okay? So because computationally, that's what we are going to be working on. And so, but generally, if we look back to the chapter 5 of textbook, it's all about analysis. 分析, analysis. Chapter 5 is all about analyzing LTI systems. So that is to say, if you're given a difference equation, you know how to analyze its spectral, its frequency response, gain and phase responses, and so on, for analysis. So chapter 5 is that. But later, blah, 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 later, probably after spring break, we will start learning how to design such a system, design versus analysis. Okay? So later in this semester, when we go to chapter 7 of the textbook, is about, so all chapter 5 is about analysis. Given a system, you can analyze its behavior, you can analyze its response, analyze how that system processes your signals. That's analysis. But design requires a different mindset. Okay? Design. We say design a system. So what do we mean design a system? You might be given some requirement, okay, maybe some performance specifications. Okay? When you are given a set of specifications, then how do you design basically your difference equations so as to satisfy those requirements? Okay? So different mindset, analysis, design. I think for most of the analysis, some of you might have learned it from signal and systems. So for analysis, we'll introduce some tools. And the main computational tool for analyzing these difference equations is the Z transform. So Z transform, the Z transform or the Z transform will show up. Okay, you'll learn where you'll review Z transform. So most of that probably has been covered by signals and systems. But then when we further move on to chapter 7, it requires a different mindset. And chapter 7 really is the core of this course. So 我们这门课的核心 is all about design. Okay, now you learn how to, after we learn how to perfectly analyze a system, then now we need to think about the opposite. If you're given some specification, how do we find the system that's optimal, that optimally satisfies your purposes? Okay, so we'll cover that much later, right? So that's a bit of an overview of where we're at. We're at lecture 4 right now. Okay, are we ready? Okay, so chapter 4, D2C conversion. As a bit of a recap, we have learned that the effect of sampling will be like that in the frequency domain. Okay, so that's to say you're given an original signal in time, continuous time, and when we sample it by multiplying our signal with S of t, and take the Fourier transform, the continuous time Fourier transform. Okay? The result is going to be, the original spectrum is going to be one component, but then we would shift the spectrum by integer multiples of the sampling frequency to the right and to the left, sum over all k. Okay? Some of them, they all interfere. They all add up. They sum up, and there's a normalization factor. So it's easier to understand. We just, when we have a signal in time, and let's say after Fourier transform, it becomes a band-limited spectrum like that. Usually that's just an illustration. It's band-limited between 2 pi b and minus 2 pi b if the horizontal axis is big omega. Okay? So that's an assumption. If our signal is band-limited, and then when we sample it by multiplying our signal with S of t, so this sequence of spikes now is denoted as x after sampling is the original signal times S of t. That's after sampling. And we've spent much time to convince ourselves that the effect in the frequency domain. Now, if we take the Fourier transform of this, then now moving on to the frequency domain, the spectrum of xs becomes the original one plus any shifted copies that occur every at integer multiple of your sampling frequency, omega s. Okay, so one to the right, and you know what I mean. Extending. Let me just draw you one more copy. So right here, we should have another one right here. Okay, and the point is that if the spectrum is band limited, then and if omega s is greater than 2 pi b times 2, okay, so if omega s is greater than 2 times the bandwidth, then we are okay, right? Then according to Shannon-Nyquist theorem, we are okay, because this triangle does not interfere with that one. They don't overlap. There's no overlap, we are okay. Okay? We're okay in what sense? We're okay in that we can retrieve the original spectrum by applying a low-pass filter. We can reconstruct the original spectrum by applying a low-pass filter. So that is to say, if we think of a low-pass frequency response that has a cutoff frequency, ideally at 2 pi b, or should I say at omega s divided by 2, okay? If you just apply a low-pass filter with cutoff frequency, with a bandwidth, an ideal one with a bandwidth of Nyquist frequency. Sampling frequency divided by 2, that's the Nyquist frequency. Okay? So we just apply, we just call this ideal response a low-pass filter. And give it a name. So let's name it H. Right. So we just apply this ideal filter. So that is to say, if in the frequency domain we apply multiplication. So we define now, probably next page. So imagine that now we define, if we just multiply, this. We just multiply the yellow spectrum with the low-pass filter response. We just multiply. Then it should be obvious that by doing so, we will be able to just keep the middle one. Just keep it, and everything else outside the bandwidth is rejected. 被拒绝了, is rejected. Okay? You see what I mean? So just by multiplying with this our spectrum in the frequency domain with this frequency response of constant gain in the passband, and we suggest that the gain, if the gain happen to be t, okay, so you should see that the result will be a perfect reconstruction in the frequency domain. The result will be, let me just use this, yeah. We just get back whatever that's in the passband. Everything else is rejected, right? So we just get this part. Everything else is perfectly rejected, all zero everywhere. So that's the same as the original spectrum. Okay. Original spectrum, yeah. So we can get back the original spectrum. So that's the idea. Can we agree on that? You take the product of H with our yellow spectrum, you get back just the original. Okay? Yeah. Let me add one line because, yeah, the reason is because the spectrum after sampling is, as we previously studied, it's going to be a sum of all the shifted copies of our spectrum. The very reason is that there is a 1 over t here, there is a t here, so everything becomes normalized. We get back the original spectrum. Can we agree on that? It's very, very simple. Very, very simple idea. Keeping the middle part. Keeping the middle part. So, so a few remarks. It should be clear. Hopefully, this is clear to mostly everybody. Yeah, can we move on? Can we agree on that? This is clear that we get the reconstruction, 重建, reconstruction. But then, second remark, multiplication in the frequency domain is what? Is convolution in the time domain. And this is the action what we call filtering. Okay? So let me clarify. At least in this course, filtering means multiplication in the frequency domain, like that, multiplying two spectrums. Maybe one is the frequency response, this other really is the spectrum. But multiplication in the frequency domain is called filtering. Right? So we preserve this terminology to multiplication in the frequency domain. We filter, water filter, coffee filter, but in this course, filtering specifically means this kind of thing, multiplying two spectrums or two frequency responses. So this is called filtering, and by the convolution theorem, that's what I just mentioned, we can achieve filtering by convolving what? By convolving this guy's inverse Fourier transform with this guy's inverse Fourier transform, right? Multiplication in the frequency domain, convolution in the time domain. So yeah, by convolution theorem, we can achieve filtering by convolving the XS, convolving the spikes, the sequence of spikes. Basically, that's the sequence of spikes that's that. We're going to convolve this sequence of spikes, denoted as XS, with the inverse Fourier transform of the frequency response because of convolution theorem. To achieve this filtering effect, what we need to do back in the time domain is to convolve the spikes, each having different height, right? Each having different height. Convolving this sequence of spikes with the inverse Fourier transform of that. So that's what we're going to work out next. Okay? So the next thing we're going to work out is what is the inverse Fourier transform of ideal low-pass response. Whatever is the inverse Fourier transform. Okay? So is that making sense so far? Everything making sense so far? Yeah? Right, so we have another terminology coming up, right? So the inverse of this frequency response is called the impulse response of the system. Okay? So specifically we're going to call the question now is, what is the inverse Fourier transform? That is that of H. We need to calculate this. And there should be a normalization factor. Okay? What is that? Yeah. And we call the result impulse response. Okay? We call the result impulse response. Yeah. Okay. Is that clear? So we are going to calculate this inverse Fourier transform next. Right? Yeah. By the way, okay, pi fs. Okay, so let's do a bit of a calculation. I've shown you the result. So just jump into the conclusion. The result is going to be in this form. The result will be sine over sine of that over that. Okay, sine of this term, pi t divided by big T over pi t divided by big T. So then we are going to show this. Let's show this. Let's show this. Okay, so remember H, what is H? H is the ideal low-pass response, right? So it has a constant gain of, if I remember, T in between in between, what's my notation? In between, what? What's my notation? In between 这个 pi fs doesn't really matter. And 0 elsewhere, okay? And 0 elsewhere. So we just insert this to that expression. Therefore, the inverse Fourier transform denoted by small h is by definition 1 over 2 pi. Now the integral can go from minus pi sampling frequency to pi sampling frequency, right? Because everywhere else it's 0. Okay, it's 0 everywhere else. So we do this, and t times e j big omega t d, and accumulating all the components in the frequency domain. That gives us back something in the time domain. The result is a time domain signal, right? So far so good? And now what's going on right here? So here, so basically we're going to be 1 over 2 pi, and big T right here. I'll move the T to the outside, and here we are just going to find the integral of this function. Integral with respect to omega. Okay, so we know that the result should be there is a jt in here. So let's write jt in here. 1 over e to the same thing, jt omega, and we need to calculate the difference, evaluate this expression at what's the notation? Omega equals to minus pi fs, and omega equals to pi fs. That clear? Yeah. So we need to calculate a difference. That's one calculate difference. So I'm going to copy this to 2 pi t, and then jt down there, and we calculate e to the plus jt pi fs, j small t pi fs, minus e to the that, minus jt pi fs. Okay? E to the minus jt pi fs. So far, so good? Yeah? So let's try to continue. Over there, okay? So still I copy everything here, t 2 pi j small t. But now this expression equals to 2j sine of that, right? 2j sine of the exponent, right? Because it's e to the j theta minus e to the minus j theta, right? This entire thing is a theta, is an angle, right? So we know that for sure, it's going to be 2j times sine whatever that's inside here, t pi fs. Pi t fs. Okay. But what is fs? Sampling frequency is 1 over big T. Right? Sampling frequency is 1 over big T. So that's why this fs is 1 over big T. So things are coming together finally. Yeah? Do we have everything together? So now the final expression. Some cancellation. There's a j right here, 2 right here, 2 right here. So we find that the result is sine pi t divided by big T divided by pi t, and we move the big T to the bottom. So that's the result. That's the result. All right. So that's a kind of short, brief derivation showing that the inverse Fourier transform of the ideal low-pass filter if our ideal low-pass filter is constant gain in the passband, 0 elsewhere, that's which is ideal. You can imagine this is ideal scenario, very ideal. And then the inverse Fourier transform will show up once many times. The inverse Fourier transform is the sinc function. Or if you are super careful, you should say this is the sinc function for t for non-zero t. So what happens when t is 0? Any suggestion? When t is 0, any suggestion? This is important. When t is 0, there are many different ways, but for when t is 0 is 1. Okay? Because this expression is not well defined when small t is 0. This expression cannot be evaluated at time 0. Okay? So we need to add this by either by L'Hopital's rule. L'Hopital's rule. You can convince yourself that when t is 0, this the impulse response is going to be 1. Okay? So at this point, it might be good for us to take a plot to try to make a sketch of h of t. Shall we do that? Shall we do a sketch of h of t? What do we mean a sinc function? Okay, so let's just be sure. The sinc function, we have sign on top, so therefore we expect that at integer multiply, this should be 0. The sinc function will become 0. And we already know that it's 1 at time 0. It's 1 at time 0, and then not pi. And then because the period of this sine function is 2t, I believe, 2 big T. So at integer multiple t, this h of t, the sinc function in that expression, it should cross 0 at integer multiples at t, 2t, 3t, and so on. Okay, integer multiple, 整数倍. Also, same thing on the negative time side. At minus 1t, minus 2t, and so on, the sinc function should cross 0. And it should also approach 0 as time approaches infinity. It converges. Okay, it should be clear because of this term. Sine is So this is rather straightforward. Hopefully you'll be able to convince yourself that it's going to be alternating in the time domain, fluctuating plus or minus, and with gradually decaying envelope like that, alternating between positive and negative, and then this envelope gradually goes down. Okay, the envelope gradually goes down. You can imagine in infinity, this sinc function approaches 0. So that's a simple sketch. Any question right here? Time domain, frequency domain is the ideal one. Okay, frequency domain, just for the benefit of showing. A frequency domain is a constant gain in the passband and 0 elsewhere. Ideal low-pass filter. Ideal low-pass filter. Frequency domain, time domain, right? Is that clear? Is it clear so far? Yeah. Okay, so we have drawn the sketch. And next, now, if you just contemplate on what we have so far, now take a look. We are applying the filter to just keep the middle part and achieve reconstruction. And by reconstruction, we know that in the time domain, we got to convolve what with that sinc function? We need to convolve something with that sinc function. So can you point out what signal do we need to convolve with the sinc? Which one? Which signal do we convolve with the sinc? Is it the original one or the spikes? The spikes, right? We are going to convolve this sequence of spikes with the sinc function. So next, let's do a sketch. Okay, let's do a sketch of and see what's going to happen when we convolve the sequence of spikes with that sinc function in the time domain. Okay. So let me try to erase this part. So we are going to convolve. So with that, we know that we are going to convolve. So if I blow up, or should I do the math first? Let me do the math first, okay, before drawing. So look at the spike. So we know that the sequence of spikes can be expressed as the original signal multiplied with S, okay? This is correct. But here I want to suggest another expression. 换种方式来写. Let me suggest another way of expressing the spikes. The spikes, let me just write down first, and you will tell me if it's making sense. The spike can be expressed also as an infinite sum. An infinite sum of what? Of spikes. 讲废话. The spikes can be expressed as the spikes. But I mean, each spike, if this is spike number 1, spike number 2, spike number 3, that's what I'm going to say. Okay? So it's going to be a lot of spikes, each shifted by nt. Yeah? And then each spike has a different height, different value, right? And what is the value? The value is the nth number. Do you see that? Because this is after sampling, right? So at each moment, the spike has a value that's a result of sampling. So this is an alternative expression I'm going to suggest to you right here. 另外一种表达方式. Okay, let's try this expression. And then mathematically, we can study what's going to happen when we convolve this. Now we are ready to convolve this. So therefore, by convolution, now by convolving, let's say our reconstruction. Actually, let me change the notation. Let me rename the result of reconstruction by letter R, where R stands for reconstruction. R stands for reconstruction. Okay, so now we are ready to see when we convolve this with the sinc function h of t. And we call the result reconstructed signal. Of course, we know that supposedly this is going to be the same as the original signal, supposedly. Because in the frequency domain, we have convinced ourselves, supposedly xr is equal to xc, okay? Supposedly, put a question mark. And it is true, it is true. But then, now I want to share with you that this expression is pretty cool because we substitute xs with this new expression. Then what we have is just copy everything right here. And we are going to convolve it with h of t. Right. So what's next? The next is we know that convolution is linear. So we can move this inside. Okay, we can move ht inside the summation because convolution is linear. Convolution is linear, so let's move h to the inside. And we also know that convolution is commutative. So it doesn't matter put h in front or put h in after, okay? So far so good. This equality holds because convolution is linear. So we move the impulse response inside the summation. Inside summation and also xn does not depend on t, right? So it's further moved inside the parenthesis, 在括弧里面 parentheses. We move HT all the way inside these parentheses because of linearity. Because of linearity, we can move inside. But then, what's cool about this? What is anything convolved with a delta function? Anything convolved with the delta function is the function evaluated at the time, right? Yeah. No, I'm sorry. Anything convolved with this delta function is the function shifted by so much. Yeah. So now we have the final expression I want to share with you. Hn. H, now, convolving with a shifted delta function means that we introduce the same shift to H. And this is a useful expression which we are going to focus. So let me pause a bit. Let me pause for a moment. Just a chain of kind of changing our notation, and we reach this very useful expression. Okay, I claim that this expression, this final expression, is useful. Okay, photo time. All right. I love it. Okay, so why do I claim that this expression is beautiful? So now, this expression is very convenient for us to visualize what's going on when we low-pass filter a sequence of spikes. Okay, so let me explain. We know that the reconstruction is going to be summation of xn, and h of t we know is the sinc function. So maybe let me just say sinc. Okay, sinc. Oh no, probably not a good idea. Probably not a good idea. Let me just still hold on to this expression h. So what's going on? Sum over all n. So that means that we are going to shift this sinc function to the right, to the left, but then modify its height, scale the sinc function by so much, by the sample values. Now, we are going to scale the sinc function by sample value and then sum them up like that. Okay? So then we are ready to make a sketch. Okay? We are ready to make a sketch. Let's say, suppose that after C to D, now everything is in discrete time. Okay? And we have first sample, second one, third, fourth, fifth, sixth, and so on. Okay, let's just draw a few samples like that. And they're equally spaced, and so on, right? So this is x of n. And then for each x of n, we are going to create a copy of sinc and put it there, put it right there. For each x of n, we're going to create a copy of the sinc function and put it right there. Okay? So that's to say, for example, for this sinc function, for this sample value, we're going to create a sinc function and put it right there. So let me use one color first. Okay? And we know that already this sinc function is going to cross 0, like that. Like that. Okay. Crossing 0, crossing 0, crossing 0, like that, and so on. So that's the first sinc function we're going to put right there. And similarly, for all the other samples, can you work out? Okay? For all the other samples, I invite you to put more copies. So let's do that together. So for the next sinc function, I'm going to create. It's going to be right here, 0 crossing. 0 crossing, 0 crossing, 0 crossing, 0 crossing, like that. 0 crossing, and going smaller and smaller. Okay? That's the second sinc function I'm going to put right there. So that's what I mean. That's what we mean. Seriously, that's this expression. That's all this expression is about. Yeah? So when we make a sketch, you can imagine, now you can start imagining, how about this one? For this one, let's do a few more. Okay, let's do a few more. So for that one, I'm going to create a sinc function that's scaled to the height, to the sample value. We're going to create a copy of the sinc function which is scaled to the sample value. So needless to say that it's a sample value like that, 0 crossing, 0 crossing, 0 like that. Maybe bigger, smaller, smaller, you know what I mean. So for now, we can move on, maybe create one more copy. Okay, for the next copy, we are going to again create a sinc function. We call it sinc function, scale to the sample value, and it's going to cross 0 like that. Okay, and so on. Okay, so now can you just imagine in your head? Okay, when we look at this plot together, when we all look at this plot together, can you see what's going on? Can you start seeing what's going on? It seems that we are going to create a smooth summation. The summation should be smooth. The summation the summation should look smooth. Should look smooth. For the next one, maybe here is another copy. Here is another copy of a sinc function. Here's another copy of a sinc function. The summation is going to be smooth, and it will further pass this. It will pass through all the sample values. Obviously, the summation of all the sinc functions is going to go through all the sample values. Why? Because the 0 crossing are so nicely placed. Because for each copy of sinc function, it crosses 0 perfectly at the sample times, but at all sample times. So not only is the result going to be smooth, if you can agree with me, but also the result is going to go through all the sample value, at discrete times. So in this sense, what are we doing? In this sense, we are interpolating. 我们是在做内插. In this sense, this is why I say low-pass filtering is interpolation in time. So essentially, we are given the sample values, and when we reconstruct a continuous time signal, and we have convinced ourselves that the continuous time signal after reconstruction will go through all the sample values like that. Okay, so it's a kind of interpolation, right? We are given the sample values at discrete times, but then we are able to sort of figure out what's missing. Figure out what's missing by summing up all the sinc functions. We can figure out what's missing. Figure out the values in between samples. Reading between lines, something like that. Okay? That's interpolation. That's interpolation. That's interpolation. Okay? All right. I think in daily life, sometimes indeed we do interpolation. 日常生活有时候会用一些内插法。Can anybody give me an example? Okay. Think about it. In your daily life, what are the circumstances when you interpolate your data? For example, if I tell you let me just random. If I tell you this is actually true, when I was 12 years old, my height was 144 centimeters. That's me, 12 years old. And when I was 13 years old, my height increases to that, still pretty short. I have poor nutrition or something. At 13 years old, right? And then, fortunately, I grew so much. 14 years old. Yeah, this is actually true. 15, yeah, that was me. That was my chart, okay? So that's sampling, right? We don't measure our height continuous time signal. No, we don't do that. We measure it once in a while, maybe once a semester, because that's sampling with a sampling period of 6 months, right? But now, if I tell you that's my height in discrete time, and if I ask you what's my height, what's teacher's height at 12 years, 6 months, can you evaluate? Then you do interpolation, right? I'm not suggesting that you should do sync interpolation. No. But I mean, generally, maybe you should sync interpolation. But yeah. But that's what we mean interpolation. Given the sample value at discrete times, then we can try to figure out what's in between in time. So that's what we mean interpolation. Okay, if I ask you what's my height at 12 years, 6 months, you will probably make an estimate. Maybe just add them up and divide it by 2, right? Yeah. So whatever strategy you have, that's interpolation. 你可能有不同的策略, but that's interpolation. You may have different strategies, but here we are suggesting that a perfect reconstruction can be realized by this kind of sync interpolation. It's a band-limited interpolation, right? Now this is just a suggestion, okay? Now, you know what? When I was really short. As a 6th grader, I was like always sitting in the front row. Pretty short guy. And then what happened in between here? This is a real true story. My mom found some kind of protein drink, 蛋白质饮料. How many of you have your mom feed you protein drinks? 有没有小时候喝这个? Yeah. And then I grew 12 centimeters in 1 year. But the problem is that the protein drink was really, it doesn't taste good. It tasted really badly. So I stopped drinking it. Then I slowed down. And I regret. Just had I kept drinking that drink, I might be Professor Zheng Guizong now. I'm sorry for myself. Yeah, I made a wrong choice. Sometimes in life you made the right choice that I regret. Okay, what's the password? What's the password? 1810022, 好，谢谢。Okay. Then what's going on right here? All right, so we just to conclude, what do we have? Still moving things around, okay, So essentially, I hope I have covered everything. The sync function, DC conversion really is a kind of interpolation by the sync function. And be careful, we need to define sync 0. One way is to show you that by L'Hopital rule equals to 1, that's one way. And so we have drawn a sketch, okay, of the convolution of the XS with HT, okay? Long story, but we have made that sketch over there. And here's my suggestion. We want to write XS by this expression, this alternative expression. And thus we have that. Okay, So next page. Okay, so next is just something to say. So if you are interested in more reading materials, please refer to the textbook. So here is one plot one figure in the textbook, and so we start with our sample values, and if we know the sampling period, we are going to first convert the sample values to XS, and then apply a ideal reconstruction filter in the time domain, in the continuous time domain, and the result is XR. Okay, so and the entire thing right here. The entire thing goes from discrete time back to continuous time, and it is called D2C. Okay? It's called D2C. It's nothing much to explain right here. And so now, also from the textbook, now the entire chapter 4 is about converting from C to D, converting from D to C, and the rest of this semester, we are going to focus on whatever that happens in between. Okay? But whatever that happens in between, but from the outside, the input could be in the continuous time, output is also in continuous time, right? So in the outside, it's like equivalently, we have an analog system. But inside is digital, okay? So this process is called digital processing of analog signals, okay? Or discrete time processing of continuous time signals. So this idea is called processing continuous time signals in the discrete time domain, in this discrete time domain. So that's one plot from the textbook. And so let's take a break, okay? Let's take a break of 10 minutes. Okay, right. Okay, so let's resume our lecture. In this final slide, I'd like to show you, there's one more slide after this, okay? There, actually in the handout, there's one more slide after this. I think I can skip this for this semester, yeah. So talking about some practical issues when we do D2A conversion. But here, let's look at this question together. Yeah. Now we process continuous time signals in discrete time domain, in the discrete time domain. What are the advantages? What are the advantages? Why do we even care? Why historical people go to the develop digital signal processing? What's the advantage? Why don't we, if the input is in analog, output is in analog, why don't we do everything in analog? That's a wonderful idea, right? Just design VLSI or put vacuum tubes, BJT, stuff like that. What's your opinion? Why? What are the advantages of doing this? Too hard to compute in analog. So you mean it's possible to compute, but it's too hard. Why? But even, yeah, is it possible to compute in the analog domain, you think? That's a very open question. All right, let's break this down. So your comment is that it's too hard to compute in the analog domain. You are right. It's rather easy to compute in the digital domain. We all do that all the time, computers, right? But can we compute in the analog domain? Yes or no? Yes, please raise your right hand. No, please raise your left hand. Right hand, yes, it's possible to compute in the analog domain. How? Huh? Like crunching, that's the gear like that. But I think that requires manpower. Okay, yeah. It's quite possible, but it's just people stop doing that. Right. Any other comments? Very good one. Okay. Is it possible to compute in the analog domain, Yanru? Oh. In. Okay, cool. So it's referring to Professor Marvin Chang's work and his lab. They do computation in memory. Yeah, very good.
Just do it
In the real world.
like building a circuit or something.
Okay, so let me be more specific. So my first job, another life choice to share with me. First choice, I stopped drinking that drink. That's one choice. Second thing, which I don't regret, by the way, the second choice, when I just got my PhD from Stanford, so I interviewed with a few companies before I decided to stay in academia, 留在学术界. So indeed, I had a few interviews. In one interview, I don't even remember the company's name, and I'm not sure if the company is still there. It's a startup company at Silicon Valley. What they do is analog computation, analog multiplier. Yeah? Digital multiplier, you can imagine, to do it purely digitally, it requires so many transistors, right? But they claim that they could, within a few transistors, they can compute multiplication. So 乘法, analog multiplier. So historically, it's been possible. Some kind of a well-known analog circuit. You can do multiplication with analog hardware. Okay, yeah. So, but then we sort of agree that it's possible to do computation in the analog domain. But what's the advantage to do it in the digital domain? What are the advantages? What are the advantages? it might be wasting you more area or more energy, right? But why is it still preferred? Why should we still consider digital computation? Yeah? Easier to design. And it has more jobs. Think so. I heard that in Taiwan, there are more digital jobs than analog. Yeah, easier to design. Okay, any other opinions? Any other issues we should consider when we decide if you build a system, you do build the analog or digital? Yeah. Most of the devices are in digital. So it has a more better ecosystem if you want to apply tools and Oh, I see. Easier communication between devices. That's a good point. Any other thing? Yeah. Oh, source. Yeah, that's true too. Yeah. Analog memory. Yeah, that's true. Yeah, thank you. Yeah. Okay. One more issue I want to touch is the noise issue. Analog circuit can be full of noise. But when we convert an analog signal to digital, we sort of control our noise to just the quantization noise. That will introduce some error for sure. But after things go to digital, then there will be no noise. Purely within the discrete time, the digital domain, there will be no noise. Or noise is easy to manage. It's easier also to manage noise in the digital domain than analog. So that's my experience. Okay. So thank you all for the comments. So indeed, hopefully this kind of discussion motivates us to move on and talk about chapter 5, talk about chapter 7. Right? Thank you. So now I'm going to conclude this lecture and move on to lecture number 5. Can my TAs help me a bit? Lecture 5. 下面是 lecture 6. That's 6 though. I need 5. Yeah, please help me. So let's take a like 1 minute break. Okay, cool. All right. Okay, so I'm going to erase the board before we move on. Huh? 我们跑可以啊，谢谢。Okay, so let's move on to the next topic. Okay, so in this lecture we will study linear and time invariant systems. And as I mentioned to you, you'll find that Z-transform is a very powerful tool for analyzing the behavior of LTI systems. But first thing, what is LTI? What is linear and time invariant? So that's the preferred thought. We need to clarify some terminologies. And then we will introduce officially the Z-transform, okay? Right, so now let's start. So here is the first notation. Suppose that we use this script H, 草写的, script H to denote a system, okay? When we say a system, we mean that the system receives an input and produces an output. So output is a kind of a mapping of the input. And this mapping is denoted by script H, 草写的 H, script H. So that's the idea. So now we can discuss a few properties. There are two properties that are of interest. The first property is linearity. The first property is linearity. Suppose that if we linearly combine two signals, and the system produces an output that is also the same linear combination with the same linear coefficients of the output. linear combination of input, linear combination of the output. If this property, if this equality holds for any given input, x1 and x2, and any given constant alpha and beta, if the equality holds for any choice, then if the equality always holds, then we say that the system is linear, right? Linearity. And then there's another property. Now, if we shift the signal to the right by m samples, the result is the same output, basically the same output, but also shift with the same that many samples. Okay? If we shift the signal by 3, the output also shifts by 3. If we shift the signal by 5, the output also shifts by 5. If we shift the signal by 1 year, the output also shifted by 1 year, same amount. Then in that regard, the system sort of stays unchanged. It's always the same system. Whenever you are going to use it, it's always the same performance. Okay? If that's true, then we say that the system does not vary against time, or simply the system is time-invariant. 不随时间而变而改变 Because the relation between input and output is basically the same whenever you use this system. Whenever you apply the system to process your signal, the result is always the same. It's just shifted the same amount of time. Okay? And such are the two properties that I will now introduce. Now, just naturally, if a system is both linear and time invariant, two properties, then we call that the system is linear time invariant, or LTI. Okay, is that clear? Yeah? So here is a kind of sort of a small exercise. So here we sort of imply that these are two properties, right? Two separate properties. So you probably can guess that there must be some examples of a linear and not time invariant system, or a time invariant but not nonlinear system. And you are right, okay? There are such examples. Some systems are nonlinear but time invariant. Some systems are linear but time varying. Both are possible according to the mathematical definitions. Okay, so maybe I can leave that. You are right. You are right. So I will leave that as an exercise. Okay, it's possible to have such examples showing that these two properties are indeed separate properties. Okay, we need to separately define them. Okay, now I'll leave that as an exercise. Okay. Any comments so far? So far, so good? Two properties? Yeah. And now, we introduce the very important concept, impulse response. Okay? Impulse response is the system's, if a system is generally, for any system, not necessarily LTI. Generally, for any system, the impulse response is defined literally, 就像字面上的 literally defined, literally 字面上的 Very good word to know, literally. Literally, 字面上, what is impulse response? Literally, it's a response to an impulse. Okay. Now, literally, impulse response is a response to an impulse. To what impulse? Delta function. Okay? So literally, the impulse response of any system is defined as, okay, this is a notation I sometimes use, defined as, okay, using a column, 用冒号, column equal, H of n is defined as any system's response to delta as the input, okay? So a system, if we give it the delta function as the input, and the result is denoted as H of n. We refer to it as impulse response. property. Okay, so now this is probably the most important message in this lecture. Okay, so let's read it carefully. Now, if we focus on a system which is LTI, then its output, it produces output when receiving any given arbitrary input. It produces an output that equals to the convolution of x, your input, with h, your impulse response. And that's a property, okay, which holds for any LTI system. And this property actually requires a proof. Okay? This property actually requires a proof. It's beautiful. And it's probably the most important property I'm going to introduce to you. I'm just going to cover for today. Okay? Let's repeat. If a system is both linear and time invariant, two properties, if the system has these two properties, then the output of the system when it receives any input is going to be equal to that input convolved with the impulse response. And what is impulse response? Impulse response is literally the response to delta function. Okay? And that's a property which requires some derivation. Okay? Or you can even call it a theorem. Yeah. Okay, so I forgot. Do I have the derivation in the handout? No, I don't. So we need to work it out on the board. Okay, we'll work it out on the board. So this requires some check, some derivation. Okay, so how do we derive it? But conceptually, it tells us that if we receive delta, which is 1 at time 0 and 0 everywhere else, okay? If at time 0 we receive one unit impulse, okay? Then the impulse response, let's say h of n, let me just randomly draw an arbitrary h of n. Let's say this is my h of n. Let's say if this is my h of n, okay, maybe one more sample right there. Yeah. If this is my h of n, which has this many samples and 0 everywhere else, okay? So we're claiming that now if we receive any arbitrary input, now when we receive any arbitrary input, what's going to happen? What will the output be like? What will be the output? The output, if we receive any input sequence in discrete time, the output should be convolution of x with h. That's what we mean. Okay? Equivalently, so we're saying that equivalently any LTI system requires the knowledge of the impulse response. Okay? Then, when we convolve the input with the impulse response, the result is the output, which equals to, yeah. That's what we mean. That's what we mean. It means that all you need to know about an LTI system is h of n. All you need to know. This is all we need to know about any LTI system. Because once you know it, you know how to process the signal. Okay? So this is the importance. H of n, all you need to know. All you need to know. Okay? All right. So now we need to convince ourselves that this is true. All we need to know about a system that is both linear and time invariant, all we need to know is its impulse response. But how do we show that? How do we show that? How do we show that? So my suggestion is we are going to consider what's happening when we feed hx into our system, okay? But let's again use this notation, okay? First thing, my first suggestion is to begin with the fact. As a matter of fact, what is x? X is the summation of all its samples, right? X is the summation of all the samples located at time k, summing over all k. Can we agree on that? A signal is a convolution of itself with the delta function. Yeah. Or the sum is the signal, the whole is a summation of parts. 全部是部分的总和啊。But this is true. Okay, so it's going to be useful, more convenient if we rewrite xn as the sum of all its samples. Okay. Is it okay? Yeah. This notation. Yeah. So now finally, then what is the output? The output is to process our input with H, our system. That you say is we are going to process our signal with the system. Like that, okay? But then, H is both linear and time invariant. Okay? So we're going to see then how to proceed. What's the next step? If now we say H is both linear and time invariant, so which property may we apply first to move on? What property, which one? Do we apply linearity first or time invariance first? There's a summation, right? So that implies maybe we try linearity. Okay, let's try linearity. So because H is linear, therefore we can move H to the inside of summation. We can pull, or equivalent, we can pull the summation to the outside because of linearity. And because of linearity, let's move the H to the inside. But as much as the time index n is concerned, H processes this part. This is actually a coefficient. Yeah. This is just a coefficient that does not depend on n, right? So when we process H of this scaling factor times delta, we know that the result should be still, we can further move H to the inside and put xk to the outside. Okay? H of delta n minus k. Yeah? So in both steps we apply because of linearity. Because it's linear. So now we are ready to move on, right? Because H is not only linear, but also what? But also time invariant. So now if H receives an input that's delayed by k samples, what's going to happen in the output? If H receives an input delta function which is delayed by k samples, invariance means that the output is also going to be delayed by k samples, right? Yeah. So now, because of time invariance, we will copy xk here, and the output is also going to be delayed by n samples. And what is the output? Output is the impulse response, literally. And that completes our check. Because delta produces H. Therefore, when we delay delta by k samples, H is also delayed by k sample, and that completes our derivation. Okay? And this last step is because of time invariance. It's because of time, sorry for my bad handwriting, time invariance. And that gives us this final expression, okay? If a system is LTI, then the output is x the input convolved with H, the impulse response. Yeah. You want another joke? I have a lot of jokes today. Literally is a good word. Okay. Literalist. Anybody want to say what is a literalist? Literalist is a person, right, who takes things literally. 总是按照字面解读事情。字面主义者。A literalist is what is a literalist? A literalist takes things literally. 总是按字面解读。这样懂吗？Do you have a friend who is a literalist? Think about it. Well, some of you might be a literalist. 总是按字面解读的人。My translation, 字面主义者。But now the joke goes, what's in common between a literalist and a kleptomaniac? What's the common in between a literalist and a kleptomaniac? Does anybody know this word, kleptomaniac? 什么狂啊 ？maniac 啊 ？kleptomaniac 查一下。What is a kleptomaniac? And then the question is, what's in common between a literalist and a kleptomaniac? 查到了呀？有窃盗倾向、窃盗狂、偷窃狂啊。Somebody who would like to steal, 窃盗狂。Kleptomaniac. Okay. Now my question: what's in common between a literalist and a kleptomaniac? 字面主义者跟窃盗狂有什么共同的地方？ What's similar between the two? 很难啊。Yeah? 谢谢啊。A literalist takes things literally. A kleptomaniac takes things. Wow. Comma, literally. 按照字面解释，他们偷东西。What's in common between a literalist and a kleptomaniac? A literalist takes things literally. A kleptomaniac takes things. Literally. Right. Oh, very nice word to learn. What is time invariance? What is impulse response? Impulse response is response to the impulse literally. Okay. All right, remember impulse response. Take it literally. It means what it means, right? Say what you mean and mean what you say. Right? Okay, so that's we just finished a simple derivation to convince ourselves that when we have a linear time invariant system, the output is going to be the convolution of the input with the impulse response. Okay, so now another definition. Here comes another definition which is useful. Causality. Okay, yeah. All right, this get back to a new concept, okay? So we need to learn this term, causal. And the mathematical definition that goes that if a system has this impulse response, which is 0 for all before time 0. If an impulse response of a system is 0 before time 0, nothing before time 0, then we say this system, this linear time invariant system is causal. Yeah? Oh, by the way, I should emphasize that a LTI system, this is within the impulse response, which is 0 before time 0. Yeah. If the first non-zero sample is going to be happening at time 0 or afterwards, if a system has this property, then we say the system is causal. Yeah. Causal is cause. Cause, that's a noun. And causal is the associated, the corresponding adjective. The system is causal. Mathematically, if the impulse response is 0 before time 0. Is that clear? And let me say that in this course, we're mostly interested in causal systems, indeed, okay? Unless otherwise mentioned. And you'll see in a moment, maybe in the next lecture. We almost 99% of the time we focus on systems with causal responses. Sometimes we say that causal impulse response, 0 before time 0. Okay? Mostly interested in such kind of systems. And then we'll learn how to analyze the causal system as well as how to design a causal system that meets certain specifications. Let me just say that again. This is kind of the entire semester is all about designing and analyzing causal LTI systems. Yeah. That's why this is important. But then very quickly, if an LTI system is causal, then we can modify the convolution index. Now, we sum up from minus infinity all the way to n. Okay? Now, so we know that now again, still, we are in the context of linear time invariant systems, which is characterized by the impulse response, not t, but n, okay? Now, in discrete time. If a system produces yn, and yn in general, if this is LTI, we have already shown that it's going to be the summation most generally of x with respect to h, summing over all k. Yeah. Most generally, k from minus infinity to infinity. But if h of n is actually 0 for all time before 0, then that means whenever h is 0, then we don't care, right? So that's why the summation index, we can sum this index still from minus infinity to the current time. We can sum k all the way to n, because when k equals to n plus 1, and so on and beyond, this term becomes 0. Okay, the system is causal. So that's why we can sum all the way from past infinity, in the past, to the current time. Now, so the idea is to sum up, look at the history, and sum up till current time. Look at the history and sum up to current time. So in that regard, let me say this is history. Okay? Look at all the input values in the history, in the past, and then sum up to the current time. Because our system does not depend on the future. The output does not depend on the future. That's what it means. That is what is meant by causality. Okay. Let me say this again. Okay. So the way we read this summation, the way we read this expression is to think of it as a summation of the past and its influence. The past, every sample in the past, including the current sample, has its influence on the output. Okay? But nothing in the future need to be considered. That's the beauty right here. Causal system. When the system is causal, then we don't need to consider future input because the current output is not going to depend on the future. And this is deep. Okay? Because our current state is never depending upon the future. Here, the future hasn't happened. So that's kind of the philosophy behind this definition. And that's why we all only care about this kind of systems, right? In practice, in practical, in real world, in reality, every system is causal. In reality. So when we sum up, we only consider influences up to the current sample. Okay? Nothing in the future should be worried about. Is that clear? We only sum up to the current sample. Causal systems. Any question right here? Now, I want to maybe pause for a few moments. Causality 因果了，这就是因cause Okay. So with that, maybe we can move a few more. We'll see a few more slides. Okay. Now, okay. So officially, we have defined what it means to be linear and time variant, and then most of the time we are interested in causal systems. Now here's an example. Okay. Here's an important kind of causal LTI systems can be defined through difference equations like that. This is an example of difference equation. Okay? So now let's take a look. The current sample depends on the past sample values, past output. The current output depends on some feedback, so you need to consider the past two samples and sum them up with the current input. That's a linear system. That's a linear system, and if this is valid for every n, then this property does not change. It's also a time invariant system. Therefore, this difference equation like that, it defines a linear and time invariant system with input right here, output right there. Linear and time invariant systems. Okay, so hopefully you get the feeling that indeed this system is time invariant and is linear in the sense that if the input increases by 2 times, the output also increases by 2 times. That's what it means, linearity. If the input increases by 2 times, the output immediately increases by 2 times, and adding all the feedback still, you double the input, you double the output. That's what linearity means. And this relation stays the same at every moment n, so therefore it's time invariant, literally. It doesn't change with time, literally, time invariant. Okay? Can we agree that this is linear and time invariant? This equation defines the system. Equation defines the system. And we can just, on the mathematical side, it's a linear and time invariant. But on the computer side, apparently this is one line of code, right? Programming-wise, you can run it. This is one line of code. Okay, so just you're constantly given the input samples, then you can compute the output sample by sample. Receiving one sample input, producing one sample of output is computable. You can compute it with probably one line of C, or one line of MATLAB, one line of Python. Right? It's just one line. Okay? So that's why we are mostly interested in LTI systems that can be defined by difference equations like that with Yn. the current output on the left-hand side of your equation, everything else which are linearly combined in the right-hand side of the equation. Okay? Linear combination, right? So this is a very simple example. This simple example, and just I try to share with you that indeed, okay, hopefully we get to agree that this system is indeed linear and time invariant. And is it causal? Is it causal? Does the system, how about the impulse response? That's what we need to check with the definition. Right? Is this system causal? Is this system causal? Right? So maybe we can work this out. Okay? If yn, for example, if yn is yn minus 1 plus yn minus 2 plus x of n. And this system, I claim to define, this equation defines a system. And now the question is whether or not the system is causal. So causality means that we need to check something. Causality, we need to check what? H of delta n, right? The impulse response, literally. If the system, if this equation receives delta as x, if x is delta, then what's the output? Is the output all 0 before time 0? That's what we are going to ask. If the system receives delta as its input, yeah, so applying the concept you have just introduced, if you want to tell whether or not the system is causal, we just put delta to the system. Okay? Put delta to the system and it produces the impulse response literally, and we ask, question is h of n all 0 before time 0? For all times before 0. Yeah. If the answer is yes, the system is causal. Is that clear? We can ask this question, okay? So can you answer, is this system causal? When we receive delta and produce this h, is h all 0 before time 0? Yes or no? Looking like a yes, right? Consider this is a line of code. Before giving it any input, of course, the output is 0. Yeah. So in that sense, yes, the system is causal, right? So it's actually not that easy to answer, but we need to do some assumption about the initial conditions. Yeah. The system is causal if the initial condition is, wait. It depends on initial condition, but generally, maybe I'm hand waving. Generally, just you can, upon some further assumption, you can convince yourself that indeed the impulse response is all 0 before time 0. It just hasn't, our computation hasn't even started. Okay. Anyway, so this is for better or for worse, we will work on difference equations. Things probably are going to be clearer. We are going to keep working on difference equations like that. Okay? This is a main subject, 一个主要的主题了。Difference equations like that. And further, so let's stop this discussion. But more generally, I want to introduce to you some terminologies right here. So we are going to study constant coefficient difference equations. Okay, right here. Difference equations with constant coefficient, for example, this coefficient is 1, this coefficient is 1, that coefficient is also 1. These coefficients, this is 系数, coefficients are all constant, and that's our interest. Okay? We are mainly interested in any linear and constant coefficient difference equations, or LCCDE. Okay, we'll do a more general discussion on that in the next lecture. Okay, in the next lecture we are going to do a more systematic discussion on how to analyze LCCDE. Okay, but in this case, 1 is a constant, 1 is constant, 1 is constant. The coefficients are all constant. This is a linear and time invariant system. But next, I think I want to show you, at least show you the definition of Z transform before we leave. Okay. So with that, let's maybe put aside all the difference equations and talk about Z transform. Okay. Talk about the Z transform. Okay, so just a brief overview of what's going on. How will we learn next time we meet? So next week we are going to review this, but here a preview. It's okay. Here's a preview. Z transform is defined by this expression. Okay? Suppose that you have any given sequence P. Could be input, could be output, could be your impulse response. Any sequence P, where then so corresponding to your sequence, you can define a function. A function with Pn and Z being the variable. Okay, Z in complex domain. Okay, and this transform your sequence or your signal, should I say? You transfer any given signal to a complex function. A function defined on the complex plane. Z is the complex plane. Okay? Then this is the notion of Z transform. Okay? The notion of Z transform. And next week, I think I want to introduce to you the relation between Z transform and DTFT. So next time, this will hopefully will be clear that DTFT is Z transform evaluated on with Z equals to Ej omega. Or DTFT is Z transform evaluated on the unit circle. Z equals to Ej omega. That defines a circle. Okay? That's the relation between Z transform and DTFT. And actually, that's also the reason why DTFT is denoted like that. DTFT is Z transform evaluated on the unit circle. So that's the meaning. Right? That's why the textbook adopts this notation. 为什么符号这样选? That's why the textbook adopts this notation. So with that relation between DTFT and there's also a convolution theorem. Multiplication in the time domain, no. Convolution in time domain, multiplication on the Z domain. Okay, that's also true. And then we can just with any impulse response, we can define H of Z. The Z transform of the impulse response is called a system function. When you evaluate the system function on the unit circle, again, we get the frequency response of the system if it exists. Okay, so in the next week when we meet, we'll spend some time to talk about conditions. Sometimes H of Z is not well defined over the entire complex plane. We should be concerned about the region of convergence. Okay? Whether or not the region of convergence, whether or not the Z transform of any given signal exists, particularly on the unit circle, right? Because if it doesn't exist, does that mean DTFT does not exist? DTFT 有可能是不存在的, it's possible, right? But let's put it to the next week. So for today, I think it's about time. In the interest of time, thank you for being here and see you tomorrow. I heard that the sign up link has some error. How? We'll need to sign up you'll need to sign up for volunteer for tomorrow's presentation, right? So please be sure that the sign up link is working. Anyway, so I trust that TAs will figure out. Okay? 谢谢，好，今天到这边，谢谢。这个哈。 刚刚有点 struggle，就是啊。
想要